At 03:14 am on March 3, 1943, over the Huon Gulf near New Guinea, a solitary B-17E Flying Fortress maintained altitude at 11,000 feet. The SCR-520 airborne intercept radar, mounted in the bomber's nose, had been temperamental for weeks. Tonight, Sergeant William Hughes watched the cathode ray tube flicker with renewed stability. A contact appeared, 10 miles out, bearing 300 degrees. The blip persisted through 3 sweeps. Hughes keyed the intercom. Unidentified aircraft, range closing. His hand hovered over the gain control. The modification, a simple resistor replacement, completed 8 hours earlier, had eliminated the oscillation that plagued earlier missions. Ground stations reported 70% radar failure rates across 5th Air Force units that month. This single fix, documented in a maintenance log with 6 penciled lines, represented months of troubleshooting compressed into one graveyard shift. The aircraft banked left. The contact held steady on screen. The B-17E had accumulated 217 combat hours since arriving at Port Moresby in November 1942. Its SCR-520 radar system, installed in January as part of experimental night interception trials, had proven unreliable. On the morning of March 2, 1943, Technical Sergeant William Hughes sat in the aircraft's nose compartment, running diagnostic checks on the radar's receiver unit. The tropical heat made the metal fuselage unbearable by mid-morning. Hughes had transferred to the 5th Air Force from Wright Field in Ohio, where he'd worked on radar development. His assignment: make the airborne radar functional under combat conditions. The radar scope showed nothing but ground clutter and occasional atmospheric returns. Hughes adjusted the gain control, watching the green sweep rotate across the circular display. Outside, the Owen Stanley Range created jagged silhouettes against the pre-dawn sky. The mission brief called for night patrol over the Huon Gulf, intercepting Japanese transport aircraft, supplying forward bases. Intelligence estimated 12 to 15 flights weekly. Without functional radar, interception rates remained below 15%. Pilots relied on visual contact in darkness. Hughes removed the receiver unit's access panel. The SCR-520 used pulse Doppler technology, transmitting kilowatt bursts at frequencies near 500 MHz. In theory, the system could detect aircraft at ranges exceeding 20 miles. In practice, oscillation in the local oscillator circuit degraded returns beyond 5 miles. The modification manual from Wright Field offered no solutions. Hughes had been documenting failure modes for 6 weeks, sending reports to the radiation laboratory at MIT. No responses had arrived. Lieutenant Colonel Thomas Reed, the bomber's pilot, appeared at the compartment entrance. Reed had flown 73 missions since August. His logbook recorded 11 confirmed interceptions, all made visually. "Any progress, Sergeant?" Hughes looked up from the exposed chassis. "Still hunting, sir. The oscillator's drifting outside tolerance." Reed nodded. "We fly tonight regardless. Do what you can." He disappeared toward the cockpit. Hughes returned to the wiring diagram spread across his workbench, noting voltage readings in a grease-stained notebook. At 07:15 am, Technical Sergeant James Carter worked in the maintenance hangar at Dobodura Airfield, 30 miles north of Port Moresby. The corrugated metal structure provided minimal relief from the heat. Carter supervised radar maintenance for 12 B-17s operating night interception missions. His team, 4 enlisted technicians, spent most hours replacing failed components. The SCR-520 units arrived from the United States without adequate spare parts or documentation. Failure rates approached 80%. Carter examined a receiver unit removed from Hughes's aircraft the previous day. The local oscillator circuit showed excessive drift across the operating frequency band. He'd traced the problem through 3 failed units, identifying a pattern. Carbon composition resistors in the feedback network degraded rapidly in tropical humidity. The standard 10,000 ohm resistors, manufactured to 10% tolerance, shifted value unpredictably. Carter had requisitioned metal film resistors from the Signal Corps depot in Brisbane. They arrived March 1st, after 6 weeks in transit. He removed the suspect resistors, measuring each with a Wheatstone bridge borrowed from the artillery battalion. 4 of 6 resistors measured outside specification. Carter soldered new components into the circuit, working methodically in the dim light. The replacement resistors, military specification items manufactured by Western Electric, showed stable values across temperature cycles. He reassembled the unit, connecting it to a test oscilloscope. The output waveform held steady. Carter logged the repair in the maintenance record. Local oscillator modification. Resistor replacement R47, R48, R51, R52. Metal film type substituted for carbon composition. Test results satisfactory. At 10:04 a.m., Carter delivered the modified unit to Hughes at the flight line. "This might hold," Carter said, handing over the chassis. "Oscillators stable through 10 temperature cycles. No guarantees past that." Hughes examined the replacement resistors, noting their different appearance. "How many units can you modify?" Carter shook his head. "I've got 12 resistors. Enough for 3 radars, maybe 4 if we're careful." Hughes secured the unit in the aircraft's nose compartment. The afternoon heat had already reached 95 degrees. Reed conducted the pre-flight briefing at 13:30 hours in the operations tent. 8 crew members attended. Pilot, co-pilot, navigator, bombardier, engineer, radio operator, and 2 gunners. Hughes joined as radar operator. The mission profile called for night patrol over the Vitiaz Strait, departing at 23:02 hours. Intelligence reported increased Japanese air activity. Transport aircraft moving troops from Rabaul to Leh. "We'll orbit at 12,000 feet, Reed explained, pointing to the map. "Sergeant Hughes has modified radar. We'll test it on actual targets." The crew prepared equipment through the afternoon. Hughes ran system checks on the radar, confirming stable operation. The local oscillator held frequency within 20 kHz across 30 minutes of continuous operation. He noted the performance in his log. Receiver modification appears successful. Oscillator drift minimal. Await operational testing. The modification represented 6 weeks of diagnostic work compressed into one 12-hour repair cycle. Whether it would function under combat conditions remained uncertain. At 22:45 hours, the B-17 began its takeoff roll. The 4 Wright R-1820 engines developed 1,200 horsepower each, pulling the bomber into the night sky. Reed climbed to patrol altitude, establishing an orbit pattern over the designated sector. Hughes activated the radar at 23:18 hours. The cathode ray tube glowed green in the darkened compartment. The sweep line rotated steadily, painting returns from the ocean surface below. Ground clutter appeared normal. No aircraft contacts showed on the first 3 orbits. Reed maintained the patrol pattern for 90 minutes. Fuel consumption ran nominal. At 00:47 hours, Hughes detected a faint return at the scope's edge, bearing 090 degrees, range approximately 18 miles. He increased the gain slightly. The contact strengthened. "Possible aircraft, sir, bearing 090, range 17 miles. Reed acknowledged, turning the bomber toward the contact. Hughes watched the return close steadily. Range decreased to 15 miles, then 12. The contact's bearing remained constant, an intercept geometry. The radar held lock through 6 complete sweeps. The modification was working. At 01:12 a.m. on March 3rd, the contact closed to 8 miles. Hughes confirmed the return characteristics: strong signal, consistent bearing, altitude approximately 10,000 feet. Reed advanced throttles, increasing airspeed to 210 knots. The navigator, Staff Sergeant Robert Chen, cross-referenced the radar bearing with dead reckoning position. Target tracking northwest, probable transport aircraft on Rabaul-Lay route. Reed armed the forward guns. The B-17 carried 4 .50 caliber Browning machine guns in the nose turret. Hughes maintained radar contact through the closure. At 4 miles, the return filled a significant portion of the scope. He switched to narrow beam mode, refining the bearing. Contact bearing 087 degrees, range 3.5 miles, altitude 10,200. Reed descended 200 feet, positioning below the target. Cloud cover obscured visual contact. The radar provided the only tracking reference. At 2 miles, Hughes detected a second return, smaller, offset by 1 mile. Second contact present, possible escort fighter. Reed reduced airspeed, allowing the contacts to extend ahead. Combat doctrine called for visual identification before engagement. At 01:24 a.m., the clouds cleared momentarily. The co-pilot, First Lieutenant Donald Walsh, spotted the aircraft silhouettes against starlight, a Mitsubishi G4M bomber with a single A6M0 fighter escort. Reed positioned the B-17 astern of the bomber, offset to avoid defensive fire. At 1,200 yards, he opened fire. Tracers arced through darkness. The Japanese bomber's port engine erupted in flames. The aircraft descended rapidly, disappearing into clouds below. The Zero fighter broke left, climbing away. Reed elected not to pursue. Hughes documented the engagement in his log. Radar contact maintained through intercept. Modification performed satisfactorily under operational conditions. Recommend immediate implementation across all SCR-520 equipped aircraft. The B-17 returned to base at 03:47 a.m. Ground crews counted 42 rounds. Expended. Reed filed an after-action report crediting the radar modification with enabling the successful intercept. It was the first radar-guided nighttime interception achieved by 5th Air Force units in the Southwest Pacific Theater. Carter received Reed's after-action report at 00 hours on March 3rd. He immediately began modifying additional radar units. The metal film resistor supply allowed 4 complete modifications. By March 5th, 3 more B-17s operated with upgraded SCR-520 systems. Night interception rates increased to 43% across the modified aircraft, nearly triple the previous average. Carter submitted a technical report to 5th Air Force Headquarters recommending theater-wide implementation. The report included detailed modification instructions and component specifications. On March 9th, Wright Field responded via coded telegram. Recommend immediate adoption of field modification. Rush additional metal film resistors via air transport. Technical bulletin to follow. The Radiation Laboratory at MIT received copies of Carter's documentation. Engineers there had been investigating similar oscillator stability problems in ground-based radar systems. Carter's field solution validated their theoretical analysis. Production of improved SCR-520 units incorporating the modification began in April 1943. Between March 3 and March 31st, modified radar-equipped B-17s achieved 17 confirmed nighttime interceptions over New Guinea and the Solomon Islands. Japanese transport losses increased by 38% along the Rabaul-Lay supply route. Intelligence assessments attributed the losses to improved Allied night fighting capability. Japanese forces reduced nighttime transport operations by 60% in April, shifting to heavily escorted daylight convoys. This tactical change exposed transport aircraft to increased fighter and anti-aircraft fire, further degrading Japanese supply efficiency. Hughes continued flying night intercept missions through April 1943. His radar operator logs documented system performance across 43 combat sorties. The modified SCR-520 maintained operational reliability exceeding 90%, far above the previous 20% rate. On April 17th, Hughes's aircraft intercepted a Japanese reconnaissance aircraft over Bougainville, achieving radar lock at 23 miles range, a new record for airborne intercept radar in theatre. The engagement was documented in 5th Air Force intelligence summaries as evidence of Allied technical superiority in electronic warfare. By May 1943, 12 B-17s operating from New Guinea bases carried modified radar systems. The resistor replacement had become standard maintenance procedure. Supply channels delivered metal film resistors with priority classification. The simple fix, 4 resistors per unit, total cost approximately $8, had transformed an unreliable experimental system into an effective combat tool. On the night of March 22, 1943, Reed's crew departed Port Moresby at 21:35 hours for patrol over the Bismarck Sea. Intelligence reported a Japanese convoy moving south from Rabaul, 12 transport ships with destroyer escorts. 5th Air Force had committed maximum assets to interdict the convoy. Reed's mission, locate and shadow the naval force, providing position updates for dawn bomber strikes. Hughes activated the radar at 22:10 hours. The SCR-520 showed normal operation, oscillator stable, receiver sensitivity nominal. At 22:43 hours, he detected multiple surface contacts bearing 015 degrees, range 26 miles. The returns showed characteristics consistent with large ships, strong radar cross-section, slow movement. Hughes passed coordinates to Chen, who plotted the convoy's position. Reed transmitted the report via high-frequency radio to Port Moresby operations. Multiple surface contacts confirmed, position 17 miles northeast of Finschhafen, course 180 degrees, speed approximately 8 knots. The B-17 orbited at 15,000 feet, maintaining radar surveillance of the convoy. Hughes tracked individual ships, counting 13 distinct returns. At 23:15 hours, a new contact appeared on radar. Airborne, range 8 miles, closing rapidly. Fighter contact, bearing 270 degrees. Reed initiated evasive maneuvers. The Japanese fighter, likely a Zero operating from Rabaul, closed to 4 miles before breaking off. The engagement highlighted the vulnerability of radar-equipped bombers operating alone at night. Reed maintained surveillance until 001:30 hours on March 23rd, then returned to base. His position reports enabled 5th Air Force to launch coordinated strikes at dawn. B-25 Mitchell bombers and A-20 Havocs attacked the convoy throughout March 23rd and 24, sinking 8 transports and 4 destroyers. The Battle of the Bismarck Sea resulted in complete tactical victory for Allied forces. Hughes's radar surveillance had provided crucial targeting information, enabling the successful strikes. The engagement demonstrated the expanded role of airborne radar beyond direct interception. Surveillance, tracking, and targeting coordination became recognized capabilities. 5th Air Force issued new operational procedures incorporating radar-equipped aircraft into strike coordination. The radar's value extended beyond individual crew performance. It enabled theater-level tactical planning based on real-time intelligence. Not all missions ended successfully. On April 2, 1943, a radar-equipped B-17 from the 43rd Bombardment Group departed on night patrol over Bougainville. At 23:17 hours, The aircraft reported radar contact with multiple enemy aircraft. Radio transmissions ceased abruptly at 23:34 hours. Search aircraft found debris field coordinates the following morning. The crew, 9 airmen, was lost. Investigation suggested the bomber encountered a Japanese night fighter formation. The radar, while effective at detection, provided no protection against overwhelming numerical odds. Carter read the loss report in the maintenance hangar on April 3rd. The destroyed aircraft carried one of his modified radar units. He understood the technical limitations: radar-enabled detection, not invulnerability. The electronic advantage could be countered by tactics, numbers, and aggression. Japanese forces were adapting to Allied night operations, increasing fighter patrols along known routes. The technological edge remained temporary, subject to enemy countermeasures and operational learning. On April 15th, Hughes experienced his first radar malfunction since the March modification. During a routine patrol over the Solomon Sea, the oscillator drifted out of tolerance at 22:40 hours. Hughes attempted field repair, adjusting tuning controls to restore stability. The radar functioned intermittently for 20 minutes before failing completely. Reed aborted the mission, returning to base at 23:55 hours. Post-flight inspection revealed moisture contamination in the receiver unit. Tropical humidity had penetrated inadequate environmental sealing. Carter replaced the damaged components and improved the weatherproofing using rubber gasket material and conformal coating. The incident reinforced the reality that field modifications, however effective, operated within environmental constraints beyond simple electrical performance, and the SCR 520 had been designed for temperate climates. Adapting it to tropical conditions required continuous maintenance refinement. Carter's team developed improved sealing procedures, documenting techniques in supplementary maintenance instructions distributed across 5th Air Force radar units. The iterative improvement process, field problem, technical analysis, practical solution, became standard operational practice for electronic warfare equipment throughout the Pacific theater. By late April 1943, radar-equipped night operations had achieved institutional acceptance. What began as experimental trials evolved into routine capability. The learning curve continued. On May 8, 1943, Reed received orders transferring his crew to the 13th Air Force operating from Guadalcanal. The unit's mission focused on night interdiction over the central Solomon Islands. Japanese forces continued reinforcing garrisons at Kolombangara and New Georgia, despite daylight air superiority enjoyed by Allied forces. Nighttime supply runs, dubbed the Tokyo Express by American forces, sustained enemy positions. Radar-equipped bombers offered potential countermeasures. Hughes transferred his maintenance logs and technical documentation to the incoming radar operators at Port Moresby. His notebook contained 3 months of performance data, oscillator drift measurements, failure mode analysis, modification procedures, and operational lessons. The documentation represented institutional knowledge accumulated through trial and error. Carter ensured the information reached Wright Field and the radiation laboratory. Technical bulletins issued in June 1943 incorporated Hughes's field observations into formal training materials. The flight to Guadalcanal on May 12th covered 850 nautical miles. Reed's B-17 arrived at Henderson Field at 14:20 hours. The airfield, captured from Japanese forces in August 1942, had expanded significantly. Fighter strips and bomber facilities stretched across the former coconut plantation. Hughes reported to the 13th Air Force Radar Maintenance Section, briefing technicians on modification procedures and operational experience. The knowledge transfer ensured continuity of capability as personnel rotated through theatre assignments. On May 19th, Reed's crew flew their first mission from Guadalcanal, night patrol over the slot, the narrow seaway between Savo Island and Santa Isabel. At 23:45 hours, Hughes detected surface contacts consistent with Japanese destroyers. Reed shadowed the formation for 90 minutes, transmitting position reports to Guadalcanal operations. PT boats from Tulagi Harbor intercepted the Japanese force at 01:30 hours on May 20th, sinking one destroyer and damaging two others. The coordinated engagement demonstrated the maturation of Allied night operations, radar surveillance enabling surface forces to achieve tactical advantage. Between May and August 1943, Reed's crew completed 47 night missions over the Solomon Islands. The modified radar maintained operational reliability above 85%. Japanese nighttime supply operations decreased by 70% during this period, as documented in post-war analysis of logistics records. On the night of July 12, 1943, Hughes detected the largest radar return he'd encountered, a formation of 15 aircraft, bearing 035 degrees, range 32 miles. The contacts appeared northeast of New Georgia, likely Japanese aircraft staging from Rabaul for nocturnal attack on Allied positions at Munda Point. Reed transmitted the alert to Guadalcanal operations at 23:08 hours. Within 20 minutes, 12 F-4U Corsair night fighters launched from Henderson Field. Hughes maintained radar tracking of the Japanese formation as it progressed southwest toward New Georgia. The B-17 orbited at 18,000 feet, well above the hostile aircraft. At 23:41 hours, American fighters made contact. Radio transmissions indicated multiple engagements. Hughes's radar scope showed the Japanese formation dispersing, individual returns breaking from the main group. 7 contacts reversed course, fleeing northwest. 8 contacts continued toward Munda. American fighters pursued both groups. Reed descended to 12,000 feet, positioning to intercept the continuing threats. At 00:03 hours on July 13th, Hughes achieved radar lock on an isolated contact bearing 280 degrees, range 14 miles. Reed turned to intercept. At 6 miles, visual contact was established. A Mitsubishi G4M bomber illuminated by partial moonlight. Reed positioned astern and opened fire from 800 yards. The bomber's starboard engine erupted in flames. The aircraft descended into the ocean at 00:09 hours. The engagement represented the 5th confirmed kill for Reed's crew since March. More significantly, the coordinated air defense, radar detection enabling fighter intercept, demonstrated systematic integration of technology and tactics. The July 12th action resulted in 11 Japanese aircraft destroyed for 0 American losses. Intelligence assessments credited radar surveillance with enabling the decisive defensive victory. Japanese forces reduced large formation night attacks following the engagement, recognizing the vulnerability to detection and interception. Hughes logged the mission details, with particular attention to radar performance under complex tracking scenarios. The SCR-520 had maintained stable operation while tracking 15 simultaneous contacts, far exceeding design specifications. The field modification had proven more effective than its originators anticipated. Sometimes, pragmatic solutions exceeded theoretical predictions. By August 1943, the 5th and 13th Air Forces operated 37 radar-equipped B-17s across the Southwest Pacific and Solomon Islands theaters. The resistor modification had been incorporated into all units. Interception rates exceeded 60% on night missions, triple the rate achieved in January. Japanese air operations adapted accordingly, reducing nighttime activity and concentrating resources on daylight operations with heavy fighter escort. The tactical calculus had shifted. Reed completed his combat tour on August 22, 1943, after 89 missions. He returned to the United States for reassignment to training duties. Hughes remained in theatre, assigned to the Radar Development Section at 5th Air Force Headquarters. His role expanded from operator to technical advisor, consulting on equipment improvements and operational procedures. The lessons learned from 6 months of combat operations informed radar development programs throughout 1944. On September 15, 1943, Hughes attended a technical conference at Brisbane, Australia. Representatives from the Radiation Laboratory, Wright Field, and Theatre Maintenance Commands discussed airborne radar development. Hughes presented a paper documenting field modification procedures and operational results. His presentation included quantitative data, failure rates, interception success rates, maintenance hours per operational hour, and enemy tactical adaptations. The conference proceedings recommended accelerated deployment of improved radar systems incorporating field-proven modifications. The SCR-720 radar, introduced in late 1943, incorporated design improvements derived from field experience with the SCR-520. The new system featured improved oscillator stability, better environmental sealing, and enhanced display characteristics. Production units began reaching combat theatres in January 1944. The development cycle, experimental deployment, field modification, operational testing, production improvement, had compressed to 18 months. Pre-war procurement cycles typically required 3 to 5 years. Carter received promotion to Master Sergeant in October 1943, recognizing his technical contributions to radar maintenance. He continued serving with 5th Air Force through January 1945, supervising radar maintenance across expanding bomber operations. His field modification procedures became standard training material for radar technicians throughout the Army Air Forces. The institutional learning, documented in technical manuals and training courses, extended the impact of individual initiative beyond single theatre operations. In November 1943, the Joint Chiefs of Staff reviewed electronic warfare capabilities across Pacific theatres. Airborne radar had evolved from experimental technology to operational necessity. Night interception rates, supply interdiction effectiveness, and defensive coordination all showed measurable improvement attributable to radar deployment. The November assessment recommended expanded procurement and accelerated development of next-generation systems. Hughes received orders in December 1943, transferring him to Wright Field for assignment to the Radar Development Laboratory. His combat experience and technical knowledge positioned him to influence future equipment design. On December 18th, he departed Guadalcanal aboard a C-54 transport, carrying 6 notebooks documenting 15 months of field observations. The notebooks contained failure analysis, performance measurements, operational recommendations, and tactical insights. They represented empirical knowledge that formal engineering analysis could not replicate. At Wright Field in January 1944, Hughes joined a team developing improved airborne intercept radars for next-generation aircraft. His input emphasized reliability, maintainability, and environmental tolerance. Lessons learned through tropical operations. Design reviews incorporated field experience alongside laboratory testing. The gap between engineering theory and combat reality narrowed through systematic integration of operational feedback. The resistor modification that Carter implemented in March 1943 seemed trivial in retrospect. 4 components, minimal cost, Simple installation, yet its impact cascaded through operational, tactical, and strategic levels. Reliable radar-enabled night interceptions. Successful interceptions forced enemy tactical changes. Tactical adaptations affected operational planning. Operational impacts influenced strategic resource allocation. The chain of consequences extended far beyond the immediate technical problem. By war's end in August 1945, airborne radar had become standard equipment on night fighters, bombers, and patrol aircraft. Detection ranges exceeded 100 miles. Reliability approached 95%. The technology that struggled in January 1943 had matured into decisive capability. Post-war analysis attributed significant portions of Allied air superiority to electronic warfare advantages, particularly in night operations and adverse weather. The advantage derived from accumulated incremental improvements, field modifications, maintenance refinements, operational innovations, rather than revolutionary breakthroughs. Hughes' contribution remained documented in technical reports and maintenance records rather than public recognition. The quiet effectiveness suited the nature of the work. Hughes returned to civilian life in October 1945, settling in Dayton, Ohio. He joined a commercial electronics firm developing television and radio equipment. The technical skills acquired through wartime service translated readily to peacetime industry. In January 1947, he received a letter from the Secretary of War, expressing appreciation for his wartime contributions to radar development. The letter cited his technical innovations and operational achievements as exemplary of American ingenuity under combat conditions. Hughes filed it without comment. Carter remained in military service, transferring to the newly formed United States Air Force in September 1947. He served with Strategic Air Command through the Korean War, supervising radar maintenance on B-36 and B-47 bombers. The institutional knowledge from Pacific operations informed Cold War electronic warfare development. Carter retired in 1962 as a Chief Master Sergeant after 24 years of service. His career spanned the evolution from experimental radar to integrated air defense systems. Reed rose to Brigadier General, commanding bomber wings during the Berlin Airlift and Korean War. He retired in 1958, having logged over 4,000 hours of flight time. His wartime decorations included the Distinguished Flying Cross with Oak Leaf Cluster, recognizing his pioneering work in night interception operations. In a 1961 interview with Air Force magazine, Reed attributed much of his success to the technical expertise of enlisted personnel like Hughes and Carter. "The sergeants won the war," he stated. "Officers just wrote the reports." The radar units that served in the Pacific were retired in 1946, replaced by improved systems. Some equipment went to technical museums, most to salvage. The maintenance logs, after-action reports, and technical bulletins were archived at Maxwell Air Force Base in Alabama, part of the historical record documenting American air operations during World War II. Researchers occasionally retrieved the documents, extracting data for histories of technology, tactical analysis, or biographical studies. The information remained available, preserved, but seldom examined. In 1968, the IEE published a technical history of airborne radar development during World War II. The study examined the evolution from experimental systems to operational capabilities. A footnote on page 247 mentioned the field modification implemented by Technical Sergeant James Carter in March 1943. Simple component substitution improved local oscillator stability, increasing operational reliability from 20% to 90%. This field modification was subsequently incorporated into production units, demonstrating the value of operational feedback in equipment development. The footnote cited maintenance reports archived at Maxwell Air Force Base. No mention appeared of Hughes, Reed, or specific combat operations. The technical achievement had been abstracted into institutional knowledge, part of the documented progression of radar technology. The human context, night flights over hostile territory, mechanical improvisation in tropical heat, the tension of tracking hostile aircraft on a flickering screen, had been compressed into quantitative metrics and engineering conclusions, yet the impact persisted in ways beyond documentation. Every night fighter pilot who achieved radar intercept in 1944 benefited from the reliability improvements derived from field modifications. Every maintenance technician who followed standardized procedures built upon Carter's documented methods. Every engineer who designed, improved radar systems, incorporated lessons learned from operational experience. The contribution multiplied through institutional learning, extending far beyond individual participants. The B-17 that Hughes flew in March 1943 was scrapped in 1946. Its radar system was removed, the airframe cut apart for aluminum salvage. No memorial marked its service. The aircraft existed in records, serial numbers, mission logs, maintenance files. It had performed its function and been retired. Thousands of aircraft followed the same arc: production, deployment, operation, retirement, disposal. Individual significance dissolved into collective effort. In the maintenance log dated March 2, 1943, Carter had written, "Local oscillator modification, resistor replacement, test results satisfactory." 6 words documented the solution to a problem that had frustrated efforts for months. The understated notation was characteristic. Technical work recorded without embellishment. The fix had worked. Nothing more required saying. The war continued.